Okay, so before the class begin, I think you guys can upload download all the MariaDB notebook, the RSQL, R Markdown, and the lab demo FDA file, the R Markdown, and the HTML file from the canvas. So since the data sites are really huge, so I'm not going to run lively during the class. So it'd be better if you can go through the HTML file with me during this lab session. Okay, so I think it's time to begin. And my name is Fiona Fangyu Li, and here today I'm your TA for teaching about how to use database in SAS R. So by the end of this lab, you'll be able to run the SQL directly on R data frames for quick ad hoc analysis and work with the real database from R. You can create tables, joining, and filtering, and using parameters safely. And you can finally write the dplyr or dbplyr and automatically translate the SQL language. Translate to the SQL language. So the heavy lifting happens only in the database. So why do we need to learn how to use SQL in R? Since I think pretty much all of you have already familiar with SQL or not. Do you? Yeah, I see someone nodding. So probably you are very familiar with SQL. So why we have to learn how to use SQL in R? Because SQL is a really common language for data. Whether you're pulling from clinical warehouse or public health registries or product logs, data lives in database. If you can query with SQL from R, you can work anywhere. And it has scale and speed. R is great for modeling and visualization, but databases are built for big joins, filtering, and aggregation. So letting the database do the heavy work makes your analysis faster and more reliable. And third, it is reproducible and it supports collaboration. So a clear SQL plus R pipelines are easy to share, review, and schedule. So the same code can run on your laptop today and a production database tomorrow. And here's how we're going to learn today. So we'll start with the quickest entry part, the sqldf on the data frames, then set up to the DBI connection. We can use the RSQLite first, and then the RMariaDB for the real live demo. Sorry. And then we finish with the dplyr and the dbplyr, so your R verbs can compile to the SQL. We'll finish with a small realistic demo that cleans and visualizes the FDA adverse event data. Along the way, I will highlight when to choose each approach and a few performance tips like indexes and parameterized queries. So we can now set up. Let's load the packages we need. If the packages is installed, you can uncomment this line and install the package once. So for the part 1, how to use SQL on a data frame with the command sqldf. The big idea here is right now we'll pretend an R data frame is a database table. So with the sqldf package, we can write pure SQL to query it. This is perfect when your data is ready in memory and you want quick and ad hoc analysis without setting up a database. So we'll use this built-in empty cars dataset. It stores the car's name in row names. You can fill the dataset using the will command. So you can say that it stores the car names in row names, but SQL expects every field to be a column, so we'll copy the row names into a column called model. So here we copy the row names to a column, to a real column. And here are 3 queries. The first query is a pure SQL query. So you use the select the order by and limit. Using the select, just pick a few columns and sort by the miles per gallon in the descending order, so highest first. And we only want the top 5, so we limit 5. So this query tells how you to quickly check what are the most fuel efficient cars. And here's the result of the first query. So this 5 cars are the 5 most fuel efficient car. And the second, we can use the filters, the where, between, and in. So in this query, we want to keep cars with MPG between 20 and 30, and we only want to use the cylinders in either 4 or 6. So this is the SQL way to say, give me a slice of the data that meets these rules. And the third query is using the groups and aggregations. We use the group by and the having. So we are grouped by number of cylinders and compute two metrics. The first one is the average MPG and the number of cars in each group. So we compute the average MPG as the name avg-mpg and count as n. And then we'll use the having command here to keep only groups that have at least 7 cars. So these are the simple SQL language and syntax. And if you are already familiar with the SQL stuff, you can treat it as a review session. So here's a small exercise. Oh, here's the answer. If you are able to open the R Markdown, you can try that for 1 or 2 minutes. So this exercise asks you to show the top 5 cars by horsepower per cylinder. So a little hint is that you can select the columns, the model, horsepower, cylinder, and you can create your own horse per cylinder variables here. So I'll give us about 30 seconds to 1 minute to think about this question. So if you're new in class, I'm using the RSQL R Markdown file, and we are doing the first macro exercise of the sqldf. Okay, so this is pretty simple. So for saving the time, I'm just copy paste the answer here. So for this exercise, we want to select the model, the horsepower, cylinder, and we want to create a variable called horsepower per cylinder using this compute 1 times horsepower divided by cylinder. And from the empty cars table, order by the horsepower per cylinder, highest come first, and we only want 5 top cars. So why we have to have this 1.0 exist instead of only the HP dash cylinder? Because it forces numeric division and avoids integer quirks in some SQL engines, and it's a handy pattern when creating ratios. So, oh, sorry, I didn't. Never mind. You can just read the HTML file. Yeah, here's the result of this macro exercise. So a quick recap here. In part 1, you saw how to run the pure SQL on an R data frame with a sqldf command. Use this when your data is already in memory and you want some fast answers, like filters, sorts, and the top key K and the grounded summaries. Next, we'll move to the real database. So we can talk about the connections, the joins, the parameters, and indexes, the tools you need for larger or shared data. So for the real database, we are going to use the DB connections and, oh, this is not, and the RSQLite. Sorry, this is a tuple here. Our SQLite package. So this ensures, first, why we use the SQLite instead of sqldf in the part 1. This is because it ensures scale and speed. It is persistent. It ensures safety and performance and portability. So in plain English, you can treat the DBI as the R driver standard for database and our SQLite as the engine we'll use today. So now we'll open a database connection. For a clean demo, I'll use an in-memory database, so it will disappear when we are done. If you want it to persist, you can change it with a real file name. Here we created 2 tables. Also, here we use the dbconnect command here. This is a default command. We create the con as the connection, and the dbconnect our SQLite to connect the SQLite server. And after that, I'm creating 2 data tables here. The first one is the car with all variables, and second one is the brand with a simple brand. So you can write, after creating these 2 tables, you have to write these 2 tables inside the SQLite. So this is the command to how to write it to inside the SQLite. You use dbwrite table. Con is the connection, cars is the name you created, and cars is the table we created. So after we write these 2 inside the connection, you can use the dblist tables con to see what are the connections here. So I'm not gonna run this because I have a MariaDB connection connecting right now. So if I'm running this stuff, it will ruin my live demo. So you can just check about the HTML files here. So if we check for the dblist tables, it will show 2 tables here, which you just read it into the SQLite. And if you want to check how many variables or how many fields in the cars table, you can use dblist fields, and it will show all the variables here inside the cars table. So next, we're moving to the query part. So we can run the same SQL you would in any database. The database does the work and R just get the results. So the dbGetQuery is the command we use inside the DB connection to get the to write the SQL language inside R. So this sent the SQL string. The dbGetQuery command sent the SQL string to the SQLite engine through the DB interface and returns the result as an R data frames. And the work happens inside the SQLite, not in R, so it can leverage database features like indexes, query plans, and streaming. So the first query is just a simple select with filter and sort, and here's the similar results as we had in part 1. And the second is the inner join and aggregation. So this is a bit tricky since we bring out a new idea called join in this database. So we want to select the B as brand and cons as n models, average as the average. We select from cars. This means we start with cars as the left join. So the join brands B using model just means an inner join with table brands alias B. Matching rows where cars model equals to brands model. So the using model is just a shorthand for on cars model equals to B is the brands model. And the inner join semantics means if a cars model has no match in brands, then the row dropped. If you want to keep all cars regardless of brand, then you should use the left join instead of the inner join. And here's the results for the inner join and aggregation part. So we just join the 2 tables, the brands table and the cars table by the model. And move to the parameterized query. Okay, so the parameterized queries are safer and reusable. What you are seeing is that we are running the same SQL twice, but instead of hard coding values in the string, we pass them as parameters. So parameters are placeholders in the SQL that get their values safely in R. And you can see here. So we create this minimum MPG for the as the parameters, and we use the semicolon here, and we create the C as the cylinder. So if we want to run this query twice, we only have to set the params equals to the list. You pass a name list that matches them. So you can also have this question mark as the placeholder, but I recommend you guys to create a real name like the minimum PG or sys, since it would be more clear than the question mark. So these two query are the same, since we just changed the number here, and we won't change the whole SQL query. And the last thing about this DB connection is about the index and explain. Those are very important in the real database, and we're going to show it later in the lab demo. So indexes speeds up the lookups and joins on the index columns. It is like a book index. And this explain query plan shows what the database plans to do. So we created an index here. We use the db execute to create an index, and inside this command we set create index if not exist, and this is the index name we created on car cylinder. So here we have an index on car's cylinder. This line returns to 0 since it because the schema changes don't modify rows. So the number here only means how many rows are affected by using the db execute, and creating an index won't affect any rows. And then we have the db-get query and explain query plan. So this shows how SQLite will run the query, the select from cars where cylinder equals to 4. The key part is the detail column. It says search cars using the index here. And what this means is that the database will use our index instead of scanning the entire table. So if we move out this index, the car cylinder index, it will show scan cars. It just means it will indicate it indicates a full table scan. So since these are really small sample size of the empty cars, it won't be much difference. But in a real world problem, when the data sets are really huge, this can cause the difference between seconds and minutes. So we really want to have to create index every time before we run the queries. And here's another small exercise about creating the index. So you can try it on yourself. I'll give you 30 seconds to 1 minute to think about it. Okay, this is pretty simple as well. So you just copy paste what we have before, and you have the db execute command, and you create index if not exist. You create the names. Here the names are edX brand. Brands is the variable name, and brand is the table name. Brands brand, and we can check for the plan for a query. So after we check the plan for the query, I won't be able to run this. Let me check if I can. No, I cannot. I have to connect the DB connection. Oh my gosh. Anyways, for this db-get query, whatever, I'll just run it. Okay, so after we check for the plan for a query, it shows 2 lines. The first one is scan B using the index. What does that mean? It means scan B means we walk through every entry in B, which is the branch table. And using index here means instead of scanning the table itself, it scans an index on branch, on the branch variable in branch table. And the second line means we search cars in model equals to question mark. This means for each branch entry, it needs to look up matching rows in cars by model. This is a key lookup, not a full scan. And we using automatic hovering index means the SQL add notice you didn't have an explicit index on cars model. So it built a temporary index on the fly to speed that join. Okay. So for quick recap for this section, we connected to a real SQLite database from R with DBI. We created tables, ran the SQL, used parameters for safety, and created index for speedy. And after that, we are going to keep writing the R code, but instead of writing the SQL query, we are writing the R code, but we are still getting the SQL speed using the 2 packages called dplyr and the dbplyr. So the big idea here is we'll keep writing the regular dplyr code as in R, but run it on the database. The dbplyr package can translate our verbs into SQL lazily. It builds the SQL, but it doesn't run it until we ask for results. This is perfect if you like Tidyverse style but needs database performance and scale. So when to use the dbplyr? It is when you want a readable R pipelines, but you also want the database to do the heavy lifting. Here we, since we already have a DB connection con here, so we are gonna create 2 lazy tables that refer to the database table. So from this point, there are no data pulled yet. It still contains in the lazy table. And then we're gonna build a pipeline. This is a really classic analytic pipeline. So we first filter cars with the miles per gallon larger than 22, cylinder adding in 4 or 6. So it is exactly the where syntax in SQL. And we muted here. We muted the horsepower per cylinder. It is a computed column in select. And we select the variables we want. It is the chosen columns in select and SQL. And finally, we arrange in descending order, which is exactly the order by descending orders. So after building this pipeline, we are not run this code yet. It just builds the SQL query. And if you want to see for like what does this dplyr R code means in SQL, you can use show query command here, and it will automatically show the generated SQL code here to like run in SQL query. So in this way, in the dbplyr packages, we can translate the R codes into SQL languages. And we use collect. This is a really important command, since we can only run the R table where like analyze this data set in R only if we run this collect session. So before that, you can see there's a source SQL database, so it is a lazy table. They are not pulled yet. But if we have this collect command here, we actually pulled all the data in R, and from now on we can analyze those data sets directly from the R. And here's another example using the join and summarize pipeline. So these are also a classic analytics pattern. We join the cars to brands on model, and we group by brand and calculate the number of models and the average MPGs. This pattern, join, group, and summarize, is really important and really classic of analytics. And similarly, we will show query here, and the R will automatically show the SQL sentences, and we collect the brand summary so we can finally do any analysis here in R. So remember, the pipeline builds up a SQL recipe, but doesn't cook it until you collect or otherwise demand results. This means the database can optimize the whole query at once. And in part 3, we stayed in dplyr, but let the database ran the work. So the key ideas here is we have the lazy queries first, and we can use the SQL translation to see the SQL sentences, and then we use collect only when needed. This gives you the readable R code, SQL level speed, and portability to many backends. So really important as well. And don't forget to DB disconnect the connection whenever you're done. So those are the basic concept of using database in R 3 ways: the dplyr, the real database, and the sqldf. So before we wrap up, I want you to have a quick look at the MariaDB. Here, I created a notebook here. You can just access it through this link. So this is really important in the real life database. And everything we just did, like the DBI, dbplyr, joins grouping, and parameterized queries, transfers directly to the MariaDB. So think of a SQLite as our teaching bag. It is simple, local, great for prototypes, but the MariaDB is the road bag you use in the real world. So it supports multi-user, secure, and it's durable, and it is fast at scale. So how does it relate to what we already know? You have to install it first, and in the terminal part, and starting the MySQL root here, and you want to create a database. Those are all completed in the terminal demand, and the only thing we need to swap is the DB connect. So in the previous one, the SQLite one, we have DB connect SQLite, but here we just swap the driver from the SQLite to the MariaDB. And you're gonna have the host, the users, and password, and the database name. You have to create your own in your terminal base. So you're gonna read this after the class. I really recommend that you to do it. And all your skills you learned before, like joins, the group by indexes, explain, and parameters, can transfer directly. So those show some simple example of using the RMariaDB to run the data and run the SQL query. So I've prepared this notebook for after class. It shows how to install and start a server from the terminal base, how to connect from R, and create tables, index, and parameterized queries. We may not have time to run it today, but I really recommend you to look through it and reach out with any questions. So the whole idea now is really simple. What we want to do is to keep writing the R but let a production database do the heavy lifting. Okay. Now we'll put the database skills, everything we have just learned, into a real world workflow using the FDA's FAERS data, which is the FDA Adverse Event Reports datasets. And you can find the original dataset using this link, but you don't have to do that. So this is the original dataset. So the goal here is to show how teams go from the public quarterly files. You can click like 2024, and you can see there are 4 quarters in the 2024, and we're gonna go from this public quarterly files to a queryable database and then to a quick, trustworthy analysis and visuals. This would be the same pattern you use in your internship and jobs, so you can get a basic sense of how the database is, how the workflow is doing and how it looks like. So we are going to set up and loading the packages. The data table do the fast reading, dplyr and dbplyr do the tidy pipelines, DBI and RMariaDB do the DBI connection, and MariaDB driver to talk to MariaDB, and those are the syntax stuff. And here's our knobs. The year start is, we want to fetch from the year start to the current year, and we want to have only the 5 core tables, like the demographies, the drug information, indication, the outcomes, and the adverse reaction, only the 5 core tables. And the message here tells you that the year range will be between 2024 to 2025, and the 5 tables we're going to use to analysis later. Now we're going to connect to the MariaDB connection using the DBI MariaDB connect with the RMariaDB driver. So in class, I'm pointing at a demo server, and if you want to know how to connect those, how to create your own, the host is just a local host, how to create your database name, the users, and the password and timeout, there's, you can find all the answers from the MariaDB data notebook. So I'm not go any deeper here. Yeah, I will just quickly cover the data collection and cleaning section since they aren't the focus of today's lesson. So if you're interested in how I collect data and modify these figures, feel free to reach me for a chat. So here, first, we want to ingest the data from online. Since you can see from this online database, there are tons of data sets and tons of zip file, and you don't want to download all the zip files and unzip them in your computer or in your local server, since it will be super slow and super huge. So here I just want to fetch it directly from online, from this URLs. So we construct these URLs and download the zip and unzip using the thread to the CSV. So we only focus on the CSV zip file. And this runs in a loop over year times quarter times table. If a file isn't found, we log it and keep going. And if it is found, we'll have a little check marks here. So after we bend all the rows inside, like we bend all the demos inside the demo all the drug information inside all the drug all, and we're gonna have this little message here. So it shows, okay, we find the 2024 quarter 1. The little check marks here shows the quarters that exist, and you can find there are little not found cross mark here, show that we cannot find the 2025 quarter start from quarter 3 as well as the quarter 4. This is sensible since we do not have that dataset access now. So this little message and warning here tells us the range of the data sets we're going to use. So it is from 2024 quarter 1 to 2025 quarter 2. And the end row shows the row counts per table. So after that, after fetching the data set, we're going to standardize all the columns. Since the public data drifts, so we standardize column names and tabs so joins are safe. And here are 2 important key variables. One is named primary ID and the second name's drug sequence. So the primary ID is the record key and the drug sequence is let us join the drug level rows to indications. And also we want to make the age to a numeric format. After fetching the data and standardize all the columns name, it's time to load all the standardized data into the MariaDB. So we persist the standardized table into the MariaDB, and from here on, the database does the heavy lifting. So it takes about 30 minutes to 40 minutes to run the loading code. So if you want to run it at your home, you're gonna find a time that you're like a big time slot that you're available. And the DB list tables count, as we had before, shows all the tables inside this connection. So we have demo, drug, the demography, the drug, indication, outcome, and reaction. And the colors and notes are the previous tables. We haven't get them rid of. So for a product-ish flow, since this is only for the demo live purpose, so I have the override equals to true for a fresh demo every time I show it. But if you want to use it in the industry where product-ish flow, I recommend you to do the append equals to true for every time you have new quarters data set. So if now we have the quarter 2025 quarter 3 data sets, we're gonna just write the table here and add the append equals to, so it will automatically append in this large data sets in MariaDB. And final stuff, the indexes. Since the whole data set is really huge, so we must add index here. And we add indexes on join filter columns. So we want to add them especially in the primary ID and the drug sequence. As I said before, those are really important. Those are really key variables in this database, since the primary ID and the drug sequence like appears in every tables. So here is a little bit small difference between the RMariaDB and SQLite. I don't know why, but I cannot use the create here. I cannot use the create data index if not exist this syntax in the MariaDB driver. So I'll just create a small function helper here to create the index. So that's why there are tons of codes writing the index, so you don't have to worry about those at all. And you can also verify if the index exists using this little query, and they all exist for the primary ID and the drug sequence here. So after we have done all of the cleaning stuff, so before the query, what we have done for now, we fetch the data directly from the website and we standardize it. We can add the parameters, but I didn't, since this is unnecessary for this data set. And we load it into the MariaDB and we create an index for the key records like the primary ID and the drug sequence. Now, after all the preparation, we are about to do the query. So it is similar to the SQLite. We use the dbget query command to run the query. So the first example, so every time we have the large data set, the first thing we have to do is a quick sanity check, a quick health check. I'm counting on how many reports we have by gender, by sex, and I'm keeping the common FAERS codes, females, males, unknown, and non-specified. This is just a sanity check to confirm ingestion worked and the codes look reasonable. So after the sanity check, it shows every count in each gender, and it looks right. So all of the data preparation parts worked here. And the second example is I'm gonna join the reactions to outcomes for the same report. So there are two tables, reactions and outcomes here. We want to join them by the primary ID. So here the key is the primary ID. I'm just running a simple so we can see the structure here. This shows which reaction terms appears in reports with particular outcome codes. And indexes are reaction. The indexes are the reaction primary ID and the outcome primary ID. So those indexes we created before of the primary ID make the whole process really fast. In the third example, I will align the drugs with their indications using the drug index. Here we must join on two fields, the report the report ID and the drug sequence. The primary ID and the drug sequence here within the report. Drawing only on the primary ID would mix up drugs and indications. So after we combine the drug and indication, drawing by primary ID and drug sequence, you can see from the result that the pairs, so we have like an ingredient and the road and the indication. So for example, the ingredients like ibuprofen and the road would be oral and the indication would be like pen. So this give you the this clear pipelines here to show for the reviewers. And yeah, the helpful index here is the primary ID and the drug sequence. Oh, wait. So for those three queries, they show the core workflow you repeat whenever you dealing with the large data sets, especially in the FDA where the clinical health data sets. So we first validate counts, and then we join the right tables on the right keys. And after that, we are going to aggregate for the question at hand. We count first, we join the tables, and we do the question at hand. After this analysis part, we can also use our visualization tools to deal with this data sets as well. So we aggregated, we have ggplot2, very familiar packages, and Plotrix, it is used for 3D pie charts. So first, we aggregate counts by sex directly in the MariaDB and then plotted a 3D pie. So this is a chart reports only by gender. The only math here is a group by sex. Everything else is presentation. This is also quick sanity check after loading. So after this sanity check, you can check, do our categories look reasonable, and are there any obvious data issues like unknown or unspecified. So the results here shows that female reports are the majority, with male close behind and a small tail of unknown and unspecified. In the second plot, I am now interested in the age density by the gender. So the FAERS dataset stores age with units. We have to first normalize it to years in SQL. So for months, we divided it by 12. For week, we divided it by 52, and so on. This keeps the conversion rule in the database, not sprinkled through R code. And from the results, we can see, and after we do the query here, we're gonna have this query name inside the ggplot2, and we can directly print out the results here. So from the plots, we can see the male and female age distribution are broadly similar, packing in late middle age, with only small differences in the front tails. After that, I am interested in the age density by outcome. So for the second plot, I just used the age and the gender, but for the third plot, I have to join the two tables, demographies and the outcome together. So we joined the demographies to outcome on the primary ID. You see how important it is for the primary ID, and it is really important to create index for this, so it will scan only the index instead of the whole table. And for this plot, again, we're using the SQL age to years conversion, and these answers to different reported outcomes show different age profiles. So similarly from the results, we can see that the outcome associated with the hospitalization HO here and some other serious events clustered in the older age with some categories like CA, the congenital anomaly, concentrated at younger age. So from this demonstration, we can see each figure come from server-side SQL. From this SQL language, single syntax with minimal collect here to plot. This is the common pattern in real project. We database for scale and R for visualizations. So after that, after we're doing all the analysis and the visualization part, the last housekeeping item is always close your database disconnection, the connection after you have done every work. It is good hygiene that prevents subtle bugs and some angry DBS. Okay, so it is basically everything for today. Today we saw 3 ways to use the database from R. One is the sqldf package for quick in-memory SQL on data frames. And second, we use the DBI connections. We have the RSQLite server driver and the RMariaDB driver to work with the real database. And we can connect and write and read tables and use parameterized queries and speed things up with indexes. And third, we can use the dplyr and dbplyr to your R verbs to compile to SQL, and the database does the heavy lifting while you collect only when you need. The big idea here, as I have said many times, we want to let the DB handle all the joins, the filters, the aggregations, and we want to use R for tidy pipelines and the analysis and the visualizations. So after this lab, I really recommend you to read the MariaDB notebook and try running a simple code. Use either the empty cards inside this notebook, a small simple size, or you can use the FAIR table here if you have time. So the aim is to connect the server and write a table, run one parameterized query, and at least create one index, and make a small plot from the collect end results. So this will be everything for today, and thank you very much for sticking with us this far. If anything is unclear or breaks, reach out to me anytime. I'm more than willing to help. Thank you, guys.